Flare network hydraulics and checklist for Flarenet modeling. In this video, we'll look at the various components of a flare network, the studies involved in the flare system design. We'll focus mainly on flare network hydraulics, what are the inputs required, design criteria used, simulation software which will be used, steps for Flarenet modeling. We'll also touch upon low temperature studies across the relief device. We'll analyze the results and conclusions, any further studies which are related to flare systems, and finally we'll give the link to a comprehensive checklist for carrying out flare system hydraulic design. In this diagram, you can see components of a typical flare system, which comprise of relief devices such as relief valves, blowdown valves, flare PCVs or manual vents, which are connected to the flare subheader by means of tailpipes, and flare subheaders from different regions would commingle into a common flare header, which is sloped towards a facility knockout drum. The knockout drum would separate out any liquids which may be at the inlet of the relief device or due to condensation in the flare network, and the gas or vapor phase would go out from the gas outlet line of the knockout drum, which goes to a flare stack and then to the flare tip, where it is combusted before release to the atmosphere due to any emergency venting requirement. Then there are auxiliary systems such as a purge gas to maintain positive pressure, a pilot gas to always keep the flare burning, ignition and monitoring systems, and so on. Below you can see another example of an atmospheric flare system where relief device is mounted on storage tank which operates near atmospheric conditions, which goes into a flare header. These relief devices are expected to release gas or saturated vapors which may or may not condense. In the flare header there is a collection vessel to coalesce and collect any droplets which may have condensed due to the ambient cooling, and then it goes to a flare stack and flare tip where it is combusted. The back pressure expected in an atmospheric flare system would be near atmospheric, which is very close to the breather valve set point and must be below the breather valve set point. This is one of the reasons that atmospheric flare network would be segregated from a high pressure flare network. There could be other reasons for segregation of flare network, such as toxic gases, cold gases, among many other reasons. If your plant or facility have segregated flare systems, then you have to take note and ensure that in your flare network hydraulics. The design of flare system may involve different studies such as flare network hydraulics and low temperature study, relief and vent load estimation, which is an input for the flare studies, sizing of knockout drum and liquid seal systems, radiation and dispersion studies to determine the flare stack height or to estimate the hazardous area classification, selection of the type of flare, whether it will be elevated flare or a ground flare, assisted or non-assisted, the type of ignition and monitoring system, pilot gas supply to maintain the flame, purge gas requirement to avoid oxygen ingress or backflow into the system. In this video, we will focus on the flare network hydraulic studies. Let's look at the inputs required for flare network hydraulics. The relief load and blowdown load estimation forms the main inputs for a flare network hydraulics. This involves the estimation of the rated or required flow rates from the relief device, the type of fluid, whether it's a single phase, two phase, or it may be in supercritical region, the type of relief devices, the properties of fluids, and most important, the flow rate of vapor and liquid at the device inlet and outlet. These are further listed for the governing vapor load for the flare header, the governing liquid load, the governing two-phase loads for all the individual relief devices, which are listed under individual mode scenarios. And then for the common mode scenarios where multiple relief devices would open at the same time, for example due to emergency shutdown during fire or due to non-fire initiators, power failure, partial power failures, and other such common mode scenarios. And the total relief load or the flare load are estimated and listed in such tables. In case you have multiple flare systems which are segregated, such as atmospheric or high pressure system, then such table should be prepared separately for each such flare system, so that the common mode scenarios which involve the relief device involving for only high pressure are listed for the high pressure flare load and not listed for the atmospheric flare load, and vice versa. Next input required for the flare network hydraulics is the details of pipe routing, such as the length of the pipes, tailpipes, flare subheaders, flare headers, its elevation profile, any bends, fittings, and all such details which are required for modeling of the flare network. Next, we would need the details of the flare tip from the flare vendor, which would typically involve a curve of flow rate versus pressure drop, so that we can model the pressure drop across the flare tip for the relevant flare load. We would also need the criteria which we would want to honor during the design of the flare network hydraulics. This would involve typical criteria such as Mach number, momentum, noise limit, acoustic limit or sound power level, back pressure limits, inputs such as pipe roughness of the flare network, etc. We would also need the environmental conditions so that we are able to specify and model the heat transfer effects due to ambient conditions such as ambient temperatures, wind speeds, solar radiation, and so on. So these are some of the main inputs which are required for flare network hydraulics and its modeling. Before we start the flare network hydraulics, we would need to specify the design criteria which will be used to honor for the design of the flare network. This could be based on international codes such as API or company specific codes, and these would involve a back pressure limit such as on the relief device, flow correlation which need to be used for the modeling, pipe roughness which will be used for the flare network, in case of any two-phase assessment of slug flow, Mach number limit, noise limit and acoustic fatigue limit or sound power level, momentum limit, You can refer to the checklist which is given at the end of this video for typical values for all these design criteria. The simulation model to run steady-state flare network hydraulics was first developed by Hyprotech as Flarenet model. Hyprotech also managed HYSYS process simulation software. Later, Hyprotech was acquired by AspenTech, while the intellectual property rights of HYSYS was obtained by Honeywell. AspenTech renamed Flarenet as Aspen Flare System Analyzer, whereas Honeywell renamed Flarenet as Unisim Flare. For simplicity, we will term the simulation model software as Flarenet in this video. Let's look at the capabilities of Flarenet simulation software. It can model flare network piping, which could be convergent, divergent or loop networks. So it is designed to handle the networks. It can perform the back pressure calculations, the velocity, Mach number calculations, estimate noise. Option to size the flare header with relief load, whereas tailpipe with rated flow. It can remove the liquid in the knockout drum device. It can perform rigorous heat transfer calculations. You can add various pipe fittings, so it can perform the equivalent length calculations using the 2K method. You also have option to add T's to connect different branches, where it can perform rigorous pressure drop calculations using Miller method. These are the common capabilities of Flarenet software. Things which Flarenet does not do is knockout drum sizing, radiation and dispersion calculations, which are typically done with other software such as Shelf-Red or FAST, which are the commonly used softwares. It does not perform dynamic simulations. For example, to estimate the minimum metal temperature. There are other softwares which are used for that purpose. Let's look at the high-level steps to set up and run the Flarenet model. Step 1. Start a new case. Press the File, New, enter the case description, enter the number of components of your fluid, select the thermodynamic package. Next, you can draw your network. You can use the palette, which will pop up a set of options such as relief devices, pipes, separators, bleeds, flare tips. You can build your network, such an example is given here, and then you can double click and enter the details of the relief devices and various components of the flare network and build your network. Next, you can define the design criteria using build in scenarios, and in the scenario manager you can edit this. Here you can specify the back pressure, Mach number, noise limits, so that any violations will be highlighted by the software. Next, you can define the calculation criteria from calculations and options and go to the calculation options editor. You can select design or debottlenecking mode here if you don't know the sizes of your tailpipes, flare headers, so that the model can estimate the required size. And finally, the rating mode for the final selected size. In case of an existing flare network, you would straight away start with rating mode so that it does not try to estimate the size on its own, and the size given by you is used. Next, you ensure that you are working in the relevant scenarios. You can select the different scenarios which was defined earlier. This may be an individual relief scenario or a common mode scenario, and ensures that only the relevant relief device opens for that scenario and flows into the Flare network. Next, you can check your preferences of the software via File, Preferences and Preferences Editor. You can start the calculation by pressing the Go button. And finally, you can view the results to show any violations. So you can view the results where you can see the messages in case any of the criteria were exceeded. You can see the pressure flow summaries. You can also check the flow map for any slugging issues. You can also display the results on the PFD using the selection box here. These are the high-level steps. Apart from the Flare network hydraulics, we would also be interested to perform the low temperature studies, especially when a high pressure hydrocarbon gas drops to low pressure across the relief device due to Joule-Thomson effect. Low temperature fluids is experienced, which will then cool down the downstream piping or Flare network piping and result in low metal temperatures. Let's look at what are the cases and options we can consider. The first is a fire case relief or blowdown scenario where we don't have any concern of low temperatures due to the high fluid temperature. Next, we can look at the non-fire case reliefs where there is an expansion of vapors or saturated liquids. The first option is to perform a steady state flash using Flarenet itself or other process simulator, which should also involve any rigorous heat transfer calculations involving the ambient temperatures and wind velocities. This will help to estimate the fluid temperature at the outlet of the relief device. However, this method is limited to estimate only the fluid temperature. It will not be able to estimate the metal temperature of the piping. If you want to estimate metal temperature, or if you have a concern that your fluid temperature is very low, below the lower design temperature of your piping, then you have to consider dynamic simulation software. Unisim Dynamics or Aspen Tech Dynamics are common simulation softwares where you can estimate the minimum metal temperature for such cases such as non-fire relief cases. Next, we would be interested in non-fire blowdown cases. In case of blowdown, the system inventory is isolated from by means of the shutdown valves, so inlet and outlet is closed, and the equipment vessel is depressurized. Here the system behaves differently because it is not in equilibrium. As an initial estimate, you can estimate the fluid temperature using a steady state flash by means of Flarenet or other process simulation software, which will help you to estimate the fluid temperature. However, if you are interested to estimate the minimum metal temperature, then you have to look at the next option for a blowdown case. You can use Unisim EO blowdown or Aspen Tech blowdown, which considers non-equilibrium conditions. It tries to solve three sets of heat transfer calculations, one involving the heat transfer between the phases inside the vessel, between the vapor and liquid phases, the other involving the heat transfer across the vapor or liquid zone with the surrounding, and finally the effect of any condensation or evaporation of the fluid inside the vessel. This will help you to estimate the minimum metal temperature of the equipment or vessel itself which is being depressurized, as well as the downstream flare network piping. Sometimes the liquid zone in the vessel may result in low temperatures as compared to the vapor zone due to an effect called evaporative cooling. The intent of this exercise is that the minimum metal temperature estimated during such low temperature events should not be below the lower design temperature of the piping. Once we have the results from flare network hydraulics and low temperature studies, we need to analyze those results. Such as we need to estimate the required tailpipe size to meet the criteria such as back pressure, Mach number, momentum, noise criteria. We need to estimate the required flare header and flare subheader sizes as well as flare stack sizes for the governing flare loads, again based on various criteria such as back pressure, Mach number, momentum and noise criteria. And we need to estimate the minimum metal temperature of the flare network piping for the governing low temperature cases. Finally, we need to arrive at the conclusions. Typical format for conclusion of individual relief device is given in this table. List of relief devices are given with its governing scenarios and loads, the required relief valve inlet size, the required relief valve size, back pressure at the relief valve, the tailpipe outlet size and the minimum metal temperatures. Similarly, this table lists the conclusion for individual blowdown valves. The list of blowdown valves are given here. Inventory volume which need to be depressurized, peak blowdown rates are given. Required blowdown valve or restriction orifice size is then given. Time to depressurize as mentioned. Inlet pipe size, outlet pipe size and minimum metal temperature are given. We would need a similar table for the flare subheaders and headers. List of governing flare load scenarios and the flare loads are given here. Required flare header sizes and flare subheader sizes are given here, as well as the flare header size at inlet and outlet of the knockout drum are given. And finally, the minimum metal temperatures is given. Flare network hydraulics would also give or provide inputs or starting points for other flare system studies, such as selection of the type of relief valve based on the maximum estimated back pressures, sizing of knockout drum based on the fluid composition and estimated back pressures, provide input for any radiation and dispersion analysis based on the fluid composition and rate at flare tip, selection of lower design temperatures of the flare network components based on the low temperature studies, purge rate estimation studies based on the size of the flare header. I have prepared a checklist to carry out flare network hydraulic studies. This is a very comprehensive and exhaustive checklist, and it comprises of the inputs required, design criteria to be considered, steps for modeling of the flare net, low temperature studies, analysis of the hydraulic results. These will help you to carry out flare network hydraulic studies in a way such that you do not miss out any important points. If you would like to download this checklist, then you can use the download checklist form. You can click on the link given in the description below, which will take you to the blog. You can fill in this form and get this access to this checklist. Let me know how did you find this video and the checklist in the comment sections below. I would love to hear your feedback.